Hello everybody and welcome back to the Our Connected Universe specialist track this afternoon. Is everyone full of energy after afternoon tea? It's better than I expected. Well done. We're going to get straight on into talks this afternoon. I'm really excited to introduce Andy Gelme to the stage, who's going to be talking to us about GStreamer, which is really exciting. So without too much delay, I'm going to hand over to our hacker hobbyist in chief in the track, Andy. Cheers.
Thanks, Jack. Good afternoon, everyone. It's good to be here. So as Jack said, I'm going to talk about Python and GStreamer, in particular focusing on WebRTC and RTSP. It's a fairly dense slide presentation, so there's a slide deck. If you've got a mobile device, you might want to check that out. And if I don't get through everything, or if you've got lots of questions, please hit me up anytime until Tuesday, or just catch up on Discord. But I'll just I'd like to begin today by acknowledging the Kurana people, the traditional custodians of the land on which we gather today. I pay my respects to their elders past and present. I extend that respect to Aboriginal and Torres Strait Islanders peoples here today. So, what I hope to cover is obviously GStreamer, provide a bit of an overview about RTSP and WebRTC, a bit of a refresher, just quickly provide some alternatives because there's many ways to skin this cat or solve this problem, and then do a deep dive. And because it's a lot to cover in a short time, there'll be links to source code and other things you can check at your leisure. So, when does it make sense to use GStreamer and for WebRTC and RTSP? There's lots of applications these days, teleconferencing, going out in drones, looking at surveying the world, trying to deal with things where it's an emergency situation, we've got to respond quickly, where low latency media streaming makes a lot of sense. And with AI going to everything these days, I guess to attract investors, and we're dealing with multimodal large language models now. Dealing with images and audio and so on is also a thing. And there'll be robots everywhere. And we've got robots driving around the streets in the form of self-driving cars. And so the basic pipeline is going to be to decode some media, you'll do some pre-processing on it, then there'll be some analysis, and that's something you might want to be doing in Python, and then post-process and re-encode again. And if you're going for extra points, it'd be really nice to do that entirely in the GPU, which is possible with GStreamer. So just as a bit of a distraction, for a personal hobby horse, when working across a lot of different domains, there's so many different frameworks for all these things you need to glue together. So you want to be able to take information from Internet of Things sensors, it might be combined with robotics, and then you might stream media off those robots to your back end, run it through machine learning, close the loop and send some control things back again. And all these, it's just really much harder than it needs to be these days because all these different frameworks don't interoperate very well. So I'm particularly interested in that, solving that problem, and I'm looking at GStreamer through that lens. And so I want to have a consistent set of APIs for, in this case, for media streaming. I want to be able to have those set up as a pipeline where I create the components dynamically, the GStream elements. I want to be able to inspect them and change the parameters on the fly. And so I don't want this to be a black box. And so that's why I'm diving in fairly deep on the programming aspect. So I'll just start with a live demonstration. So what's going on here is right in the middle there's an RTSP camera, there's a white box, and that's and the idea is to take the stream from that RTSP camera, run it through a pipeline, and then have that presented as WebRTC video. So the WebRTC part is all the blue parts. We have to set up our WebRTC session through the signaling server up in the top left, and so the browser has to interact with the back end through the signaling server. They negotiate, and then that allows them to set up the session. So that's roughly what we're seeing. And so fingers crossed this works, as the network's been up and down a bit for me today. But what hopefully we'll see is a WebRTC view that's being streamed to the back end and then appears on the browser. So let's see how we go. So let's go about that. So this is running against our back end. Up in the top left, there's a number of devices which we can select. So there's our office cameras, WebRTC camera. I can also select the camera on the laptop, and there's also just a mock video. And you can see in the back end, we should be able to see the processes running. So there's these devices I can look at. Yeah, I like things to be white boxes rather than black boxes. I can see inside what they're doing. And then we can see that's the RTSP source. It's just down there, we can see it's loading about 4 images a second. And hopefully what we'll see is the pipeline starting up. So it's, yes, sir? Up or down, okay. Okay, so again, select the office camera and then try and start the WebRTC session. And there, that's the view out of our office in the city, in Melbourne. It looks like a somewhat sunny day. And we can see in the back end, there's now a WebRTC session peer. There's the RTSP data source. We're doing some processing in Python and then writing that as WebRTC. So I can also select a different data source. So I can just select the web camera on the laptop. Have this come on. Yes. Do you want to fix it? I'm Vini. Okay, when you say it was yeah, sure. Okay. So, try that again. Here we go. And you can see that's taking the web camera and streaming that through our ML model to do face detection, and the Python's just putting a bounding box around it. So that's sort of the aim. Let's shut that down. Oops. Demo fail. Right. Okay. So I'd just like to quickly cover some alternative approaches. So everyone's probably pretty familiar with OpenCV, and just in roughly one page of code, you can see that we can, in orange, do the GStreamer part where we create a GStreamer pipeline as a string. We then use video capture to create an OpenCV video in object. We do the same thing for the output pipeline, and then we sit in a loop where we just read images in off video in, do a bit of processing, and write out. I imagine a lot of people in the audience have done that already. Which is nothing wrong with that approach. It gives you all the access to OpenCV. It's very simple. A little bit of a downside is dealing with those literal strings gets quite messy. However, the big problem is that you've completely lost all access to GStreamer's capabilities because you've just really got these video in, video out objects, and you can't access like meta buffers or anything else deep in GStreamer, and also doesn't work for audio. Another approach is to use FFmpeg. Also not too difficult. You once again set up these pipelines for input and output up the top, process 1, process 2, and once again sit in the loop just reading bytes off process 1, doing some processing and writing it back out. That works too. It also handles audio. FFmpeg is really powerful, but it's just a wrapper around FFmpeg, so you don't, once again, you can't leverage GStreamer. But it's still worth considering if that's what you need to do. All right. So let's get into GStreamer. So just for reference, I included how to install GStreamer on Ubuntu 22. It's getting much easier these days. A few years ago it used to be quite a trial. Now it's just you just install a few packages, set up your Python environment, install the Python G object. What that does, that allows you to access all of the G GNOME libraries on Linux. So you get to GTK and many things, and in this case GStreamer. And if you can just run through that little sequence down the bottom of importing the GNOME inspector object and then doing a GStreamer net, you know that you're successfully installed. And I'll put a link up the top to how to do that, the online instructions. And similarly for Mac OS, you just use brew to install GST Python. It's just everything's all in one big package, and it's once again very easy to test. So that's kind of the good news. I don't know how to do this on Windows. I'm sure it must be possible. All right. So let's look at RTSP now. So just a quick refresher for anyone who's not familiar. What RTSP does is it basically gives the details, negotiates, initiates talking to an RTP server. So RTP is the real-time protocol. It just wraps up a codec like H.264. It's typically used for things like network cameras, where you can get an RTP video stream. And what happens is you have your client, which is could be your Python code, and you have the orange boxes here representing the client side. where the RTSP client will make some requests on the RTSP server, which is your network camera. It'll describe some what sort of commands it wants to send in terms of play and terminate. It can set up options, which is to say what sort of channels and resolutions and things, and the play command just initiates. That then gets the RTP protocol going from the RTP server aspect of the camera, which sends your video back, and then you can just terminate and tear it down. So it's reasonably straightforward. How you can do that in GStreamer is you construct a string of pipeline elements. So you say I want to access an RTP source. I want to depacketize that to get the H.264 video codec out. Then you decode that and convert it into effectively raw buffers that GStreamer can deal with. And this string would display an RTP session up on your desktop, and at the bottom we just replace that video sync for the desktop with app sync, which is how you access GStreamer plugins within Python. So the problem with that, doing this from the command line, is that you've got no way to access the video stream from Python. So that's what we're about to get into. So how this looks from a conceptual view is there's some data structures. There's the pipeline on the left, and the pipeline consists of the elements that we're constructing, these plugins, so the RTP source, depacketizer, and so on, until you finally get to the app sync, which allows you to extract images off the pipeline. The pipeline has a reference to a bus, which has a reference to the messages which stream across the bus. These are the GStreamer buffers. So that's the first step, is to set that pipeline up. We do that by just creating the pipeline elements and then adding the pipeline and then linking them together. So the first step is we'll create the input pipeline, which takes the RTSP video and gives you an application sync to get your images. The second thing we'll do on the right is we'll create the output pipeline, which takes your app source plugin, which is how you take images from Python and get them back onto the GStreamer pipeline. And then that gives us a UDP sync, so we can pump out RTP at the end. The third step is to create a callback function called sample image. That'll take images takes buffers from the GStreamer pipeline and just converts them into images, which we can then sit in a loop and process them, and then we push those out to the pipeline again. So how that looks in code, so it's a bit of a full screen, is that at the very top, we'll construct that pipeline. The second box is where we go through each of the elements with using element factory. We create those elements. We start with the RTP source, and then we end up finally having a sync. So we're just using element factory make. The second box is we add all those pipeline elements together into the pipeline, and the third box is where we link them together. So it's basically steps are you create your elements. You add them to the pipeline, and then you link them together. That gives you your pipeline. So this is also doing the same thing for the output pipeline. The difference here is whereas in the input pipeline we start with an RTP source, and at the very bottom we end up with an app sync. In this case, we're going to start with an app source, and then we add the elements to re-encode that as H.264, redo the payload for RTP, and then we link all these elements together. Now, an alternative to doing this is just use the GST method called parse launch, which takes your string and then just immediately gives you a pipeline. In this case, I want to create the elements myself, and I can access the properties. So, for example, I want to set properties like the host and port on the UDP sync, for example. Once we've got our pipeline, we'll create this function called sample by image. The sample image will be as a callback, and so it will get called by the sync, which is the end of the input pipeline. This sync gives us a sample. We can pull out the buffer. The buffer has information like the resolution. It also has timing information, and we can then turn that buffer into a NumPy image, which we then put into a queue. And then once we've created that sample image callback, we can then just attach the sync to that by using the sync set property method. So by this stage, we should now have an input pipeline, output pipeline, and we've connected the sync to our sample image callback. And then the final step is now to run the pipeline. With our pipeline input in and pipeline out objects, we can start them playing, and then from the pipeline in, we get the bus. We're going to time out every second. That's 1,000 by 1,000 nanoseconds. And then we then sit in the loop. We pick up the messages off the bus, And I've cheated a bit here, but I haven't got the code that shows we're pulling the image from a queue, but we're basically going to pull the image from a queue. We do our Python processing. We turn that processed image back into bytes, into a buffer, and then we emit that back onto the Python output source. And we can also check messages to see if we've received an end of stream. For example, the network may have failed, or we may have got to the end of file. So after all that, you can see it's a lot more work than OpenCV or FFmpeg, which is where I started. But once you've done it, you can basically put it in a little library and forget about it. But it gives you access to every pipe element and the ability to change properties and to really delve deeply into what's going on the bus. Okay, so now for WebRTC. So WebRTC was a standard that it was a long time coming. I think it took about 10 or more years until it appeared in all the major browsers, but fortunately we're there. And it's basically ends up being in your browser a library that you can access from JavaScript, which allows you to set up your media connections to like your web camera and so on, your microphone, and then it involves a lot of a number of servers that you need to have out in the net to help you with tunneling through firewalls. But in the end, it provides you with multiple channels of video, audio, and data. They're bidirectional, low latency, which means about around a second or less, and it's secure and it works through firewalls. If you're trying to set up a network camera behind a firewall, you'd be messing around with a lot of port forwarding, all that sort of stuff. Whereas, as we've seen, WebRTC uses NAT traversal to basically get through all those problems for you. So the parts that make up the WebRTC standards, a couple of things aren't part of the standards. You'll need a web server of your own, which will provide HTML and JavaScript to your web browser. So that basically form your the client side of your WebRTC application. You need a signaling server that allows you to communicate between your WebRTC peers, because at first you have two parts of your system. Like your client server don't know how to talk to each other and don't know if they get through firewalls. So you have an external server so you can talk to them. You'll have your Python GStreamer code in a back-end server, and then you'll use probably a commercially available or freely available stun and turn server to actually help you get through firewalls. So a stun server helps two programs or two applications behind firewalls to find out what their IP addresses are and so they can talk to each other. And if for some reason you can't form a direct connection between them, you can use a turn server, which basically allows you to transfer media streaming through that external server. And it's not always necessary. You might be on the same LAN, or you might be using tailscale, something like that. So you might be able to, or also you can use NAT traversal to negotiate getting through your firewall. At the very bottom, I put a link to the GStreamer WebRTC demonstration code. So about 4 or 5 years ago, one of the team put up some demonstration code. The main issue of that code is it has some documentation, but it needs a lot more, and also you need to fill in a lot of the details. So hopefully I'll help that today. Okay, so here's a bit of a diagram about how I think WebRTC works. There's a lot of other explanations on the net, but there's the servers, the web server, the signaling server, the stun and turn server. And the first thing we need to do is get HTML and JavaScript to the browser, so that the browser can now start to initiate the WebRTC session. Once the web browser's up and going, it'll send a peer ID, like a random number, to the signaling server, and so basically to establish a session on the signaling server. And in the approach I've taken, the web browser also will connect to your backend, your WebRTC Python code, and also pass it the peer ID. And then the fourth step is your WebRTC code will then talk to the signaling server with that same peer ID, and now you've established a connection between the web browser and your backend through the signaling server. One of the surprising things about the WebRTC standard is the signaling server, which is an essential initiation part of the process, isn't actually standardized. It's up to everyone to create their own, or maybe to agree a bit. So it's probably one of the biggest problems about trying to hook up to third-party WebRTC vendors. So like it could be like Zoom, which mostly follows WebRTC, or Jitsi, or Google Meet, is that everyone's signaling server protocol might be different, which is interesting. So anyway, once you've got the signaling, once both your web browser and your Python peer is talking to the signaling server, you do what's called a service description protocol negotiation, and ICE is a protocol for helping you traverse the firewall, and you negotiate whether you want audio, video, or data channels or not, resolutions. Once you've negotiated that, you then begin trying to establish a connection. Use the Sun server for the peers to find out what their IP addresses are and see if they can talk to each other directly. And if they can't, they'll use the turn server to basically forward their traffic backs and forwards through. So how the diagram looks, the endpoint just have these purple dashed lines is effectively like a logical connection between the browser and your Python code to do the negotiation over the signaling server, and the dashed line for the media transfer is to indicate that the end result is to establish a bidirectional media between the browser and your code, which may or may not use the turn server. So it's hopefully gives you a bit of an idea about what we're trying to accomplish. So to set up WebRTC, the starting point for me was to use this GStreamer demonstration code, and over a lot of time I've fleshed that out to be more complete. Everything in WebRTC is, when you go into production, needs to be SSL, so you need to grab some certificates. It's obviously a bit of pain when you're developing to do that, but it's good to have a secure result forced upon you. I did read a few years ago there was a problem with WebRTC leakage, where it could possibly leak out information about your IP address, which wasn't a bug, wasn't an implementation bug, it seemed to be a design bug, but there seems to be workarounds around that. So it is meant to be entirely secure, but there's still issues. Enough about certificates. Then you set up your web server to run to provide the HTML and JavaScript. You then run your Python code, which I'll have a look in a sec, and then you can configure some stun and turn servers. What we did is we just used Twilio because they were cheap and very reliable. We tried using a few free ones, but found that they weren't reliable. You didn't have much bandwidth, so it just at least for commercial production purposes, it was just better just to pay a small amount of money to not pay a lot more in time and effort. And then finally, you just run your code. So it's a little bit more complicated than just talking to a network camera, but obviously got more capability. So when you run your WebRTC code, this is sort of the phases it'll go through. It'll at first so let's assume the browser's up and running by this point. You'll receive from the browser a peer ID. I've just said the golden ratio, 1618 is the peer ID, and you then connect to the signaling server. That sets up the call, so you can now talk between the browser and your back end through the signaling server to negotiate. At that point, you can start your pipelines, because the WebRTC pipeline, the plugin element called WebRTC bin includes all the negotiation, all the underlying WebRTC back and forth, like the SDP negotiation, ICE, and so on, and stun and turn. You don't have to worry about that at all. You basically just set up a number of Python callbacks, which are C++ hooks into WebRTC bin. And so you'll be told that the data channel has been created, that negotiation is needed. You can create the SDP packet, which says whether you want audio or video and what resolution. The offer goes back to the browser, and it either is accepted or rejected. And then ICE is used to set up the media transfer. And then after that, your channels are open and your video's up and running. So I wasn't expecting this to be completely clear. We'll give you a sense that there is actually quite a bit of backwards and forth, which is sort of done on your behalf by the underlying GStreamer plugins, and you can put callbacks to capture them. But it's also nice to know what this looks like. Okay, so the main thing to do is the pipeline creation, and the way you create the pipelines for WebRTC is exactly what we just went through before with RTSP. You create the pipelines through adding these GStreamer plugins together. You can see from these pipelines here that there's a lot more elements in it, but you can pretty much copy that by rote, really. You don't have to figure out all the details. You can see it's using VP8 as the codec. So anyway, steps are you create the pipelines. You link them together. You run the pipelines, and then after that, you handle the callbacks that come back from the WebRTC bin, and they're the two pipelines. So I've left some link there for the demonstration code. Plus also the framework I've been working on that's open source. I've got more fleshed out versions of this that we actually use in production, so it's a bit more fleshed out. Right. So I've just got a link in here to some of the local hackerspaces. I hope to visit the Adelaide hackerspace if we get time. And actually, I said there's going to be no time for questions, so I finished a bit earlier than I thought. So I'm going to be here until the end of Tuesday. So if anyone wants to chat more about this, because this I had to get through a lot in a very short period of time, but I'm happy to sort of show you code and show you working stuff. Please come and contact me on Discord or however. So thanks very much for listening. And Jack, if there's any questions.
Thank you very much. Now, while Chris looks for your hands in the audience to pass a mic for questions, I'd just like to say thank you, because it was fascinating to see behind the scenes of the tech that's made PyConline possible, and also what's helping all of our remote presenters come into our halls today. So thank you, that was fascinating. Chris, do we have a question?
Hi.
Fantastic.
Hello.
Maybe not specifically regarding the WebRTC Python thing itself, but in terms of the free servers for stun and /turn,
Yep.
like what did you look into that didn't work?
I looked into the free ones about, nearly 3 years ago now, so I'm not up to date. And I just found a couple we used, and they sort of worked. It was enough to develop, but as soon as we started to try and demonstrate the code and what we're doing, they just weren't reliable. Sometimes they'd be up, their bandwidth was not great, and so we found Twilio was. I don't work with anything like that, but we just found their prices weren't too bad, and they're super reliable. Typically, because stun turners don't use much bandwidth, they just way of identifying the IP addresses and your reachability. Quite often you can find free ones. Google runs a free stun service. That's not the problem. The problem is once you make your connection, is if your two peers can't talk directly to each other, they need a turn server, and then you're moving gigabytes of data over the network on someone else's dime. So, yeah.
Yeah. I was just curious because we use Coturn for our Blue Button turn server, so. Yeah, we haven't had any limitations around that just yet, but maybe we need more people hitting it.
Well, I started before the lockdown, COVID lockdown, and so I think over the last 2 or 3 years, obviously there's a lot more use of teleconferencing, so maybe that's changed the world a bit.
Certainly, I'm not sure we've got time for any other questions, but as Andy said, time for the hallway track, and have a wonderful conference talking about.
I'll just like to add one thing. I was hoping this to be a data source today, but I didn't get onto the network. But I'll be playing around with this robot with some AI if anyone wants to talk robots and machine learning. Thanks.
Awesome. Well, thank you very much for your talk.
Thank you, everyone.
And here's a thank you gift from the conference.